Hello, I'm Jack from New York University, and I'm going to be presenting our paper about our two approaches to assessing student progress in cybersecurity exercises. This paper was a collaborative multi-institutional project led by Valdemar from Masaryk University in the Czech Republic in coordination with contributors from the Evergreen State College, New York University, Lewis and Clark College, and Northern Kentucky University. The main goal was to compare two types of graphs for representing student activity in hands-on cybersecurity exercises. In addition, we verified that instructors can interpret these graphs with respect to where students did well and where they had problems. The shared purpose of our two approaches is to provide instructors and students with accurate and insightful assessments of student progress and skills developed. Our hope is that by assessing our two approaches, we can provide better tools for instructors and students to improve the quality of hands-on cybersecurity exercises. Cybersecurity students need to develop practical skills such as using command line tools. Hands-on exercises are the most direct way to assess these skills, but assessing students' mastery is a challenging task for instructors. We aim to alleviate this issue by modeling and visualizing student progress automatically throughout the exercise. The format of student data shared by both of these modeling approaches is command line bash history data. Using this data, we generated two types of graph models, shared them in a survey with computing instructors, and asked them to qualitatively evaluate their usefulness in assessing student progress, identifying difficulties during exercises, and providing feedback to the students. Overall, we found that the majority of instructors surveyed were able to effectively interpret our graph models and responded that they could identify use cases for each type of model. It is beneficial to develop general tools that allow information from different platforms to be shared. In this paper, we demonstrate how institutions with different cybersecurity learning environments can collaborate to improve their methods of assessing student progress. As mentioned, the primary requirement for generating our graph models is just that student activity data is collected in the form of command line bash history. That means that our techniques can be generalized to any environment where this data is available, even outside of the domain of cybersecurity. You can find the data used in this paper, as well as the open source software we used to generate our graph models at the Zenodo link below. With some minor configuration and modification, any command line exercise can be made to conform to one or both of the formats that we use to generate our graph models. The two learning environments that we use to collect data for this paper are CRP and EduRange, which are hosted by Masaryk University and the Evergreen State College, respectively. CIPO and EduRange share the common goals of being extensible platforms that allow instructors to create new hands-on cybersecurity exercises and then providing these exercises in an easily accessible collection. Each of our graph modeling approaches are being built into their respective platforms so that tools for semi-automated, timely, accurate, and in-depth assessment of students are easily available to instructors. You can find more information about our two learning platforms at the links below. Now onto the details and examples of our two modeling approaches. The first approach, implemented by the contributors to the CRP platform, results in generating what we call trainee graphs. Trainee graphs are produced by comparing each student's activity against an example solution, which we call a reference graph, that is created by the author of the exercise. Reference graphs can be understood as a linear series of state transitions where a student begins an exercise and the solution is a series of steps that incrementally brings them closer to the end of the exercise. The other type of graph model, implemented by EduRange, are what we call milestone graphs. Rather than viewing exercises as a chain of student actions, milestone graphs break exercises into small, independent tasks, each identifiable through unique, regular expressions, and can be completed in any order. Before we look at some examples of each of these graphs, here's a quick reminder of what we're looking to read from them. Most importantly, these graphs should be effective in quickly and accurately identifying the successes and struggles of a specific student. Trainee graphs show the detailed path a student takes during their attempt at completing an exercise, whereas milestone graphs only show activity that seems directly related to one of the expected tasks. This means that trainee graphs could be helpful to show students so that they can reflect on their approach and the path they took during an exercise. Milestone graphs may be more suited to identifying which singular tasks cause the most problems for the most students across a class. Here's an example of a trainee graph. Reading from top to bottom and left to right, we have a simplified exercise where the student has 3 goals: list the files in their directory, change to a new directory, and read a file in that new location. Reading from the red arrow leaving the start node, the student first types LD, a typo of the command that the reference graph is expecting, resulting in being tagged as erroneous. Then, leaving the start node, in green, the student types the correct ls command, transitioning to having them completed the show files step. Again, from left to right on this node, the student first uses the command cd with the incorrect argument of bad directory, resulting in an error. Then, in yellow, they attempt to read the file without first taking the step to change directories, resulting in a yellow node that indicates that they were missing some prerequisite steps. Finally, following the green arrow from the show files node, the student uses cd with the correct argument, leading them to the next successful state, which allows them to read the required file and reach the end state of this example exercise. In larger, real exercises, this is still how the trainee graphs are structured, showing the complete record of student activity as they relate to a series of state transitions that are defined in the reference graph. Thus, a student can quickly be evaluated based on how far down the chain of steps they progressed, and misconceptions, mistakes, or novel solutions can be investigated on the paths that split off from the expected solution. In comparison, here's an example of a milestone graph. While trainee graphs scale vertically with each additional step expected in an exercise, milestone graphs scale horizontally, with one column for each defined milestone. In this cropped example, there are 3 milestones as shown in the white boxes. First, to move a file, then to copy a first file, and then to copy a second file. Descending nodes from these milestones are rectangular if they are student activity that seems to be related, and ellipses are summary nodes generated at the end of each chain. In this example, the student had no activity that was able to be matched with the first milestone, resulting in only a red summary node that indicates 0 attempts and that the milestone was not complete. For the middle milestone, there was student activity detected that seemed to match this task, shown in the yellow rectangle. This node was marked as a partial attempt because the student used the incorrect command, cd instead of cp, but with the correct file. Since no other data for this middle milestone was detected, the report node at the end indicates that one attempt was made, but ultimately the milestone was not completed. Last, in the third column, the student uses the correct copy command with the correct options on their first attempt, resulting in the green rectangular node and the green report node. In a real exercise, these chains of attempts can be much longer, but instructors can quickly estimate a student's progress based solely on the ending report nodes. Milestone graphs do not show student activity that is unable to be associated with a milestone, so it is less possible to follow a student's path through the exercise. But tasks which cause the most trouble for a student will still appear as the columns with the longest chains of attempts. In terms of our research methods, we observed 20 students in the CytoCRP environment and 26 students in the EduRange environment to produce 2 datasets. Each dataset was then run through each of our respective graphing tools to produce both trainee graphs and milestone graphs for each dataset. Then, in our survey, we had instructors look at either the 2 sets of graphs from dataset 1 or the 2 sets of graphs from dataset 2. By doing this, every instructor surveyed was only looking at one of the 2 sets of students, leaving the graphing and visualization methods as the isolated variable that instructors would observe. The 2 student graphs shown to the instructors were chosen such that the student made progress overall, but had specific identifiable problems. In our survey, we asked 5 questions of the instructors. First, how would they assess a student based on the models? Then, which tasks did the student struggle with? What feedback would you provide to assist the student? How would you compare the 2 models? And on a scale of 1 to 5, how useful would these graphs be for your classes? To score these responses, we, the authors, created our own coding of how we would answer the first 3 questions based on the graphs, and we checked to see if those surveyed reached the same conclusions about the student activity. Overall, the majority of instructors did share our observations, indicating that they could interpret each graph effectively. Beyond this, the survey responders were able to identify distinct and effective use cases for each graph, and provided other feedback and suggestions for readability, such as modifying the color scheme or scaling and proportion of the graphs for larger datasets. There are 2 main limitations with our methods of evaluation and visualization that developers on each platform are continuing to address. The first is minimizing the amount of effort required to adapt new exercises to the requirements for our modeling. Trainee graphs require creating reference graphs that represent a sufficient proportion of example solutions to each step in an exercise. Milestone graphs require drafting regular expressions to cover the same solution space. Methods for automating these necessary steps would help to make adapting new exercises to our evaluation methods more accessible. Developers at EduRange are also considering how these visualization methods might be more usable in real time, either so that students can have a map of their activity as they work, or so that instructors can more easily observe their class and provide assistance in the moment rather than as a post-processing step. Some of that assistance could also be informed or even provided by a machine learning-based hint system that would be able to cluster students and identify common misconceptions. The full paper and slides used in this video can be found at the link to Masaryk University below. Supplementary materials, including all the full datasets, software, and results, including the graphs shown to participants of our survey, can be found at the Zenodo link. If you're interested in learning more about EduRange or CytoCRP and have any questions, or even would be potentially interested in using them in your classroom, please reach out to us. This paper was supported in part by the National Science Foundation and the ERDF project Cybersecurity, Cybercrime, and Critical Information Infrastructure Center of Excellence. Special thanks also to Stacy Watson for developing the file wrangler exercise used in EduRange, and Aubrey Birdwell for his work in the software used to generate milestone graphs. Thank you for listening, and we hope you enjoy the rest of the talks and papers at SIGC 2022.